Hi, welcome to StatStuff. I'm Matt Hansen. This lesson is part of an extended series on hypothesis testing in the analyze phase. In this lesson, I'll review some very critical concepts that serve as the foundation for how most hypothesis tests work in statistics. So if you don't catch these concepts, then please review this lesson again or explore other resources that may help explain these laws and concepts. As well, it may help if you've at least reviewed the prior lesson on hypothesis testing. But for now, let's talk about some basic statistical laws. There are three general laws that are commonly associated with statistics. There's the law of averages, the law of large numbers, and the central limit theorem. So let's start to explore the law of averages. This actually isn't a law, but it's usually a lay term that people give when they're unfamiliar with statistics. It represents a belief that the outcome of random events will actually even out for them. Let's go over a few examples here. First example is it's a belief that an event is due to happen. So for example, if you flip a coin 10 different times and you get heads all 10 times, then it's a belief that presumes you're due to get tails next because you had 10 in a row of heads. However, the probability of getting tails really doesn't change. It's still 50-50 as long as it's a evenly weighted coin and it has heads and tails on both sides. It's still 50-50. However, if you're getting heads 10 straight times, and since that's so unexpected, you're actually thinking it may actually be that the coin is unevenly weighted. So in actuality, there's a greater probability you're going to get heads again because there may be some bias in the coin after all. Another example is a belief that a sample's average must equal its expected value. But if you flip a coin 100 times, then there's only an 8% chance that you'll get exactly 50 heads. So you may not get exactly the expected value as you might think in flipping it. Third example would be a belief that a rare occurrence will happen if you give it enough time. For example, the statement that if I send my resume to enough places, someone will eventually hire me. Well, it's a bit ridiculous. That may actually represent, though, that may be true if it's assuming a non-zero probability and that the number of trials is really large enough. But in that case, what we're thinking or calling the law of averages here is actually simply just the law of large numbers. So let's talk about the law of large numbers here. This is a legitimate theorem, unlike the law of averages, where the average of the results obtained from a large number of samples will be close to the expected value and will be closer as you obtain more samples. So an example would be the expected average value of a six-sided die. If you have a die that you're rolling and the values for that is 1, 2, 3, 4, 5, 6 that you're going to be getting, those add up to 21, divide that by 6, then the average is 3.5. Well, there is no roll that comes out as 3.5. But if you roll the die 10 times, the average of those 10 rolls will be close to 3.5. And if the more trials or sets of 10 rolls that you record, then the closer the cumulative average will be to 3.5, even though it's impossible to truly roll a 3.5 individually. This law is actually the premise for what is the central limit theorem that we apply to statistical testing. So now let's talk about what is the central limit theorem, or CLT. Well, many of the statistical tests that we use in hypothesis testing are founded on the central limit theorem. It's an understanding of this theorem that can help us to understand the basis for most of these statistical tests. So what is the central limit theorem? Well, technically, it's the means of random samples from any distribution, whether that distribution is normal or non-normal. Given a certain mean and given a certain variance, they're going to have the following characteristics. It's going to be approximately a normal distribution. It's going to have an overall mean that's equal to each of the separate means, and it's going to have a variance that's equal to the variance divided by the number of samples. So let me walk through an example of what that really means. And the example we'll walk through is as if you're rolling some dice. Suppose you roll a pair of dice 10 times and you write down the average of rolling it those 10 times. Now if you continue rolling the dice over and over again, and with every 10 rolls that you have you write down those average, then what you should see as you continue to do that process, the averages of each of those sets of rolls will be about the same. And the more that you roll, the variance between the values will become more and more narrow. That is, there's going to be a lot less variation between them. But what if the dice are weighted? That is, what if there's some bias in it and you're not getting a fair representation, or it's a non-normal distribution? Well, you'd actually come up with the same results. Except that the difference is the average will be shifted, but even though the average or that mean is going to be shifted and be different, you're still going to get a mean, just like we saw before. You're still going to result with a normal distribution and a mean that's equal to the overall mean, and you're going to have a variance that's equal to the variance divided by the number of samples. So what can we conclude from this central limit theorem? The more samples you collect, the
the more confident you can be about what the mean is for all the samples of the population. So again, if you have on some scale, you have some line that might represent the central tendency. If you were to roll 5 sets of dice, you might get a distribution that looks like this if you're recording all the averages. But if you if you were to roll 5 more times and you have 10 sets of dice, your average is going to be about the same. And if you notice, it's going to be a little bit less variation. And then if you roll even more, you're going to have even less variation, and your average is still going to be about the same. And this phenomenon is what we're calling the central limit theorem, and again, that sets the basis for most of the statistical tests that we'll be running.
Now we'll talk more about how we can measure that confidence using confidence intervals.
Well, a confidence interval represents the range, that is the lower and upper bounds, in which the population mean should reside based off of the data that we're looking at. So let's use the example like we had before of rolling the dice. Let's say again we rolled the dice 5 different times and we record those averages. Well, we said before how the distribution might look like this. Well, the dotted lines on each side here represent our confidence interval. That is, after rolling it 5 different times, our average might be represented here as a central tendency where the hump is in our distribution, but we're 95% confident, if we're using a 95% confidence interval, we're 95% confident that the population average is going to fall somewhere within this range. As we collect more data, that is, as we rolled more dice, as we saw previously, we saw that there was less variation in our hump. It tends to be in about the same range, that is, it's around the same central area, again having around the same average. But if you notice in this example here, the dotted lines become more narrow. And it's because now we've got more data to back us up, and now we're 95% confident that the population average is going to fall somewhere within this more narrow range. And as we collect even more data, that becomes even more narrow. Now we're again still 95% confident that the population average is going to fall within this more narrow range. It's because the more data that we're collecting, the more confident we can be about where that true population average should fall. So the spread of the range is dependent on the size of the sample, how many data samples that we've collected here, and the desired confidence. That is, like, do we want 95% confidence? That's going to be much more narrow for us compared to 99% confident, which is going to be a little bit wider for us. Now remember, we've gone over before the standard error of the mean, or the SE mean. That's the descriptive statistic that's used to calculate the confidence interval. So if we wanted to get 95% confidence interval, then we just merely calculate the SE mean by 2. Or if we want to calculate a 99% confidence interval, then we just multiply the SE mean by 3. Now remember, statistics are intended to help us make inferences about a population. So let's say we have something where we have a measurement where the mean is 57 and we have a confidence interval of 55 and 59, where we're saying that the sample mean is only 57, but despite that, the actual population mean, we're 95% confident it's going to fall somewhere between 55 and 59.
So hopefully that concept makes sense. But let's explore how those confidence intervals are used in statistical tests.
Well, statistical tests will use the confidence intervals as a way to compare the confidence intervals to see if there really is a difference between factors that are being compared. So let's walk through an example. Let's say that we have 50 samples and we're doing a comparison of some value between employees and contractors. Well, among these 50, they might see a test result that looks like this, where the dot represents the actual average and the line extended on either side would represent the confidence interval. So for the employees, what we're measuring here, we might have an average of about 11 on this scale, but the actual confidence interval means it could fall for the population somewhere as low as 4 or maybe somewhere as high as 17. Where for the contractors that we're comparing them to, they have an average of about maybe 8. And their confidence interval shows it has this spread where it could be as low as maybe 2 or 3 or as high as 15. So by comparing these two groups like this, the actual statistical tests are looking for overlaps that fall within these confidence intervals. The more overlap there is, then the greater chances that the population mean is going to fall within this overlapped area. And if the population mean for both of these different groups that are separated here falls within the same area, then the statistical test will generally have a high p-value, indicating that there's a strong chance there is no difference between these. And there's a high risk of you being wrong if you claim a difference between these two compared values. That's typically what happens when it compares the overlap. But what if you collected more data? You doubled your data size now. Now for the employees, again, your average shifted a little bit it and you've still got some confidence interval on either side. Same thing with the contractors. So what the test will do is it'll again look at that overlap. Now that it sees there's a much less overlap, what's really the chance that both of these groups are going to fall within this overlapped region? The chance of it falling, both of them falling within this smaller overlapped region, is much smaller now. It's because of that smaller chance that's going to represent as a smaller p-value. So chances are you're going to have a small p-value enough to say that there probably is a difference between these. Now, we can't say exactly what the p-value is. That's part of the calculation for the statistical test. But the point is that the more samples you get, you're reducing, you're shrinking, or making your confidence interval more narrow, and by making it more narrow, there's less overlap between the compared groups. All the way to the point that if in our example again we doubled our sample size even more, again our averages haven't moved much, but we've made our confidence intervals more narrow. And by making them even more narrow, by having more samples, we can see there's no overlap. And when there's no overlap like this, our p-value is probably going to be very low, or it's going to be 0, simply because we have enough data to at least be 95% confident that there is a clear difference between these two groups, because now we have enough data to prove that difference. When we had less data, we didn't have enough to prove the difference, but now that we've got 4 times more data in here, in this example, there's enough to prove there is a difference between employees and contractors. So let's walk through another example of this. Let's say we're trying to compare the efficiency between the performance of 2 different systems. Let's say we collected 50 transactions between each system, and let's say for system A the time was about 180 seconds to perform a certain transaction, and for system B the time was about 160 seconds. And let's assume that there's a standard deviation of about 1/3 of each of these between the two systems. So on the surface it looks like system B is faster, 20 seconds faster. For the number of transactions that are being processed, that could be great, and that might be the justification we need for the system. But we have to be careful. What we really want to understand is system B statistically faster? What's the best and worst case difference in efficiency for system B? Well, in order to plot these numbers, we can use something like the sample size calculator to calculate the precision, or something like the SE mean to figure out, again, how precise we can be in these measurements. So for system A, we might say the average falls here at 180 seconds. But it might have, based off of the standard deviation and the number of samples that we have, using this, if we plugged it into a sample size calculator, then it would say we've got 16 seconds for precision. That means we have 180 seconds as our average, but the population average could be as low as 16 seconds less than that, which is about 164, or about 16 seconds higher than that, which could be as high as 196. We compare that to system B, their average came out about 160. Now, based off of their information, the standard deviation and the 50 transactions that they have, their precision is about 15 seconds. That means system B might perform on the average 160 seconds, but the population average for system B could be anywhere as low as 145 or as high as 175, somewhere within that range. Now, when you compare these two, what we're seeing, there's some overlap here. Now, this overlap could suggest in this case that they're actually performing about the same speed. It really depends on the analysis that's run, but because there's so much overlap, we probably can't conclusively say there's a true performance difference between system B and system A. They might be operating about the same. So if we wanted to be more clear, more specific about trying to see if there's a difference between the performance between the two systems, then what we need to do is increase our sample size. By increasing the sample size, we're making this confidence interval between both systems, in this example, more narrow. By making that confidence interval more narrow, there's less overlap between the confidence intervals. And having less overlap, again, means that we're more distinct in seeing the differences between the two systems, the two groups that we're comparing. And the more distinct we can make them, then chances are we're going to have a lower p-value. Having a lower p-value, again, means lower risk in being wrong, which means we're probably going to end up rejecting the null hypothesis, which is, again, accepting the alternative hypothesis.
All right, before we close this lesson, let's discuss how we can apply some of these concepts in a practical way.
Let me present this scenario for you, and then we'll ask a few questions based off of that. Let's say that you have 2 sets of continuous data that you're comparing across 2 different groups, and each set has 100 values in them, or 100 observations in each set. The first data set has an average value of 127 with a confidence interval of 117 to 137. And the second data set has an average of 132 with a confidence interval of 123 and 140. So based off of this information, again, not applying any statistical analysis on it, but just off of what we went over as a concept behind confidence intervals and how statistical tests tend to use them, see if you can come to the best conclusion you can about some of this situation. First off, would you consider those confidence intervals to be wide or narrow? Would you also expect the p-value to be high, medium, or low? And is there a statistical difference between these two data sets? Obviously, you may not have been able to apply it to an actual test, but do you think that there would be a statistical difference between the two data sets? And how confident, well, roughly, would you be in your conclusion? And how would the analysis change if you only had 50 samples in each data set instead of 100? And how would the analysis change if you were to collect 300 samples per data set instead of just 100?
Well, that wraps up this lesson. Check out StatStuff.com for many more resources that can help you achieve powerful results. I'm Matt Hansen. Thanks for watching.